Welcome to the Constellation tutorial video. My name is Dane. I'm the developer and admin for this software, which is a web application aimed at performing unsupervised detection of patterns corresponding to polymeric analytes in high-resolution mass spectrometry data. The application features several powerful algorithms designed to automate the discovery of these patterns, as well as an interactive graphing area in which both raw mass spec data and any resulting patterns can be viewed and manipulated. Constellation is open source software written in Python, and it has an interface which uses elements from the open source Dash component libraries. And all code is publicly available on GitLab, which you can see right here. Yeah, so in this video, I'll be taking you through the basics of how to use the program, including loading a raw mass spec dataset into the software, using the graphing area, assigning molecular formulas, and using the trend finder algorithms to discover any patterns corresponding to potential polymeric species in your dataset. In some following videos, I'm hoping to dive into more specifics as well as tips and tricks for getting the most out of Constellation. So for the sake of brevity, I'm going to make this video a general overview and not discuss all the various settings and parameters which are possible to configure and customize here. So first up, a general guide to the Constellation interface. First is this data and formulas section up here in the top left-hand corner, where you can upload raw mass spec data into the program, as well as perform assignment of molecular formulas. You can see that the general order of operations in the program is indicated through these alphabetized sections, so A, B, C, etc. However, this is only a suggestion. Of course, you can explore the software in whatever way you like. So let's start by loading an example data set. If you are curious about how the software works, but you don't have a data set on hand, there's an example one available up here in the documentation pop-up. If you go into the raw data upload section, you can download this example lignin data set. If you click it, it'll just download it into your computer somewhere. I've already done this, and you can see it's open right here. So Constellation requires your raw mass spec data to just be 2 columns of information, mass to charge and intensity, and labeled exactly like that. These 2 columns of information can either be tab separated, in this case, or comma delimited. You can, of course, choose either one of those. Here it's tab delimited, so I'm just going to click. I'm going to upload this already downloaded example lignin dataset. I'm going to click open, and it loads into the program. So as you can see now, the graphing area is displaying information. Before we actually explore that, we're going to quickly start the formula finder because currently it can take a little while to run, so I'll let it run in the background first. I'm going to enter an output file name. I'm just going to call it formulas.csv, and I'm just going to click start. And then you just click OK, and what it does is send a request off to our high-powered data processing server, which is running this sort of high CPU demanding algorithms. So that's going to run in the background. And now I'm going to show you what has come up in the graphing section. We've got this large graphing area which is displaying information. Currently it's in mass defect mode. So the raw HRMS data has been transformed into the mass defect space. And you have Kendrick mass on the x-axis and Kendrick mass defect on the y-axis. Each point on this graph represents a peak in the original mass spectrum, but as you can see, these peaks are now separated in a 2-dimensional mass defect space. And if you hover over or click any of these points, you can get this information on the side under hover data or selected data. You can see that information changes as I hover over the data or select a data point. Currently there is no formula or series information, but of course we are currently generating formula information and we'll be later generating series information, so you'll see that information also pop up. This plot could be in any configuration. You can zoom in on a particular area by clicking and dragging. You can zoom back out, auto scale to full. But regardless of what view you're at, or how zoomed in you are, or how you've configured this, you can download this plot as a PNG. It sort of gives you this really nice, high-quality image. And yeah, these other buttons allow you to zoom, pan, do a box selection of some points that you want to look at. You can do a lasso select. You can zoom in and out. You've got these clear and refresh buttons here. For example, if you just want to reset things. But the graph, for the most part, automatically refreshes on its own when other things in the software happen or give new information to the graphing area. And then further down on the right-hand side, we have these display options where we can change the graph mode. Right now we're in mass defect mode, but if I go to mass spectrum mode, of course, now we can look at the actual mass spectrum. Of course, intensity data on the y-axis and mass to charge on the x. Let's go back into mass defect mode. Yeah, so you have now the option here to modify the axes of the graph, which we're calling the KMD base. This is the nominal and accurate mass pair, which is going to dictate the transformation of the raw mass spec data into the mass defect space. We can change this to any custom value. This is currently set to the very, very common CH2 value, which is a nominal mass of 14 and accurate mass of 14.01565. But of course, you can change this to any custom value by clicking on custom and then simply changing this value. We'll just change it randomly here. This is a good use of the refresh button. And you can see the data changes completely. I mean, it's transformed, but you can change this to any nominal and accurate mass value pair. For example, if you find a series in the data that has a certain KMD base, you can change the graph axes to that base and then look at the series, and hopefully at that point it will be more of a horizontal line on the graphing area, allowing you to observe along the horizontal the changes in how many units of your monomer you have within a polymeric species. You have this intensities display option. Currently it's set to none, which means all of these points are the same size. So the intensity data from your raw mass spec file, this intensity column, is not actually being mapped onto this graph, at least in the mass defect mode. But we can change that by dragging this slider, and you can see now the points are transformed. Their size depends on their intensity in this column. For example, here's the most intense point in our raw MS data file. So this can be useful. Again, it's just another data layer, and sometimes it's not useful at all to add that complexity into the mix, especially if you're looking at a much bigger raw mass spec file, or you have a bunch of series that you found with Trend Finder, and it's a very busy screen. And then we have a transparency option. If you have a whole bunch of series information, which you'll see later when we use Trend Finder, it's really nice to be able to sort of fade the raw data into the background a little bit while you focus on looking at the series that have been found. You can change the color of the raw data between blue and black. And then we also have this option to preserve the zoom level. So when other changes are made in the program, or there's new series information or formula information, the graph updates. And if this is unchecked, it will always go back to this full auto scale, basically, that allows you to view all of the data in one frame. But of course, if you're zoomed in, and now we make a change, for example, to the raw data transparency, this preserved zoom will keep this zoom level. Okay, so now we should be able to see the formulas data layer in the graph because our formula finder is finished. It tells us that we found molecular formulas for 239 out of 299 peaks in the dataset. We are able to save this output file with the save button here, so that'll just download as formulas.csv. The formula finder is running algorithms from the open source Core MS software package, which is developed at the Pacific Northwest National Labs in the US. And this is the output file from that script, so it's got a lot of information in it, but what we're basically pulling out of it here is the molecular formulas that it found. And you can also load it back into the program using this upload area, or any saved formulas file that you have generated using Constellation can be loaded. And if you now roll over points on the graph, you should be able to see under the hover data and selected data boxes, you should be able to see formula information for almost every point in this data set, which is really exciting. So that's being imported, just like the intensities, as another data layer on top of this mass defect graphing space. You can also modify every parameter which the formula finder uses in its calculations under the settings pop-up window. If you click on that, you can see under formula finder settings, you've got all these settings, which I won't dive into right now, but elemental limits and such, everything to do with the formula finding algorithm is customizable here. You also have this data filtering area, which is very, very useful if you have loaded a very large raw mass spec data set into Constellation and you want to optimize trend finding parameters before you sit and wait for results for your full data set, which depending on the size could take quite a while. So if you use the data filter first by turning it on and filtering the data to a target length here, which in this case it's taking the top 300 peaks in the data set according to their intensity. So the top 300 most intense peaks. That of course can be changed to any number. And when you turn the data filter on, it'll give you this indication that the filter is on, just so you're remembering that you're not actually using your full data set. But we're going to turn that off because we have a relatively small data set here. Okay, so next we're going to look at the trend finder area, which is the heart of the Constellation software and performs the unsupervised detection of polymeric patterns in the data set. And there are two ways to use trend finder. There's untargeted and targeted modes. In untargeted mode, the settings button is disabled here and the program automatically chooses optimized settings for your data set. You have no control over which units or bases are used in trend finding. You simply enter an output file name, I'm going to call it trends.csv, and you click start, click OK, and you wait. In our case, we're using a fairly small input data set, so this calculation will not take that long, a few minutes maximum. However, with larger data sets, this may not be the case, and using the data filter can be a really good practice. So in targeted mode, you immediately have more options to take into consideration. You can see this whole new area opens up down here, and the settings button now activates. So you have this plethora of parameters available in the settings pop-up window, which we won't describe in detail in this video, but rather save for a future tutorial. And secondly, you have this new set of controls which appear just for unit and base finding, which is essentially the first step of the trend finding process that you now have more control over. So if we simply click start here, we begin the unit base finding process, which in untargeted mode was the first thing started doing automatically. But here we have full control, and after this is finished, we're able to see what potential units and bases the software was able to find for us, and they will appear in this unit base selection box, which we can then curate to our liking. We can also add a custom unit or base to this box if we want. So I'm just going to try to add a value for a custom base here. I'm going to add an accurate mass, and this is the CH2 repeating unit. I'm just going to add a custom unit base, and you can see it appears in there. And you can see this unit-based finding algorithm is giving us status updates. It's almost finished. And then it will populate this unit-based selection box. And you can see everything it found, in addition to, of course, our custom unit that we just entered. So it said it found 10 unit spaces. Of course, there's 11 now because we've added our custom one as well. But you can now curate these. You could remove, by clicking the X, you can remove any you don't like. If there's lots in here, you can actually search the box for an entry. And then, of course, the next step is to run the actual trend finding algorithm. So once you've curated this box as you like, it will use all of these as units and bases to do the overall searching. And you simply click start and OK. Like the formula finder, at the end, you're able to save the resulting data file to your computer with the save button. And also existing data files can be uploaded here in this area. You also have the option, once the process is finished, to view trend statistics, which gives you a little bit of information about the results of trend finding. So here we have results. You can see the graphing area has been updated. Like before, you can save a trends.csv file, which you've just generated. If you open it up, it includes a series number, which has been assigned to each series it found in the data, an index for each point of where that point is found in the raw data set, mass to charge, intensity, information about the unit and the base for each series, the formula annotation, the slope value, R-squared value. It's got a color associated with each series, and then it's got all the statistical information. some of which can be viewed in this trend statistics window. So it tells us 184 series were found within the data set with 8 different units and 10 bases. And of course, if you scroll down, now you have all of this information, as you can see, is a bit of a mess here in the graphing area. So one way we can sort of clean this up, because we sort of want to see what we found here, but it looks a bit messy even when we zoom in, is we have this series selection box. So section E in the program. Here we can curate the series we want to see in the graphing area in case it's too crowded, which in this case it is. If you click show hide, you suddenly have this area appear where you've got all the series that are present in the graphing area. You can see it's possible to remove any series we don't like just by hitting the X, and the graph will update and remove them. In this case, there's a lot of series. So if I just remove them all, click this X, that won't work because I'm still viewing all series here. But if I go to select series and this box is cleared, suddenly there's no series on the graph. And of course, this box is searchable. So now if I'm under select series, I can add series 1, which you can see is here. I could add series 2, which you can see is right next to it. Series 37, completely customizable. And this allows you to actually dig into the data and really see what you have without being too overwhelmed. And sort of as a final example here, I'm going to take a look at one series, series 53, click on it, select it. You can see this particular point actually belongs to a number of series, but the series I'm interested in is, of course, series 53. I want to transform the graph according to the base of this series, so I'm going to copy in those values and go to custom. Then I only want to look at series 53. I'm going to go back to auto scale. And you see now that I've set the base to the actual base of the series 53, you can see now it appears as a fairly horizontal line on the graphing area. That is, of course, depicting a change in whatever this changing unit is. Yeah, and you can see, of course, essentially how this transformation works, right? This algorithm, trend finding algorithm, was looking for horizontal series of evenly spaced points corresponding to the change in the monomer unit of a polymeric species, and it found these 3 points. Of course, I can isolate this series in the graphing area and manipulate it, which is really, really nice. I can zoom in, I could save a publication quality image, I can go back to viewing all series whenever I want, and I can also view none if I want to clean the graph up again. So that's pretty much it for the general introduction. I hope it was informative, and if you need more information, please first, if you can, refer to the documentation here, which I've written to try to guide you through the program as best as I can, or send an email to me. You can find my email if you go to the server status. It's just at the bottom of the window here. For the curious, this server status, server monitor window is just displaying the current status of the data processing server, which runs the formula, unit base, and trend finding algorithms. So it's kind of a high CPU demanding processes. If you notice this status light saying inactive at any point, please send me an email. I'd really appreciate it. I can find a way to troubleshoot and get the server back online. I'm currently the admin. And in general, I'm always interested in hearing about any bugs or issues or feature requests for Constellation. And your feedback is really helpful in making this software more functional and usable. So thank you. And have fun using Constellation, and let me know if you have any questions. Thank you so much. Bye.